What if I told you that the fundamental difference between a transformer and a multi-layer perceptron, the exact architectural debate we've spent years agonizing over, is mathematically just an illusion?
It sounds completely counterintuitive, I know, but it's true.
Right, because if you've ever spent weeks fine-tuning an LLM on specialized data, only to watch it completely overwrite its foundational reasoning skills, well, you know the wall we're hitting with current scaling laws.
Oh, absolutely.
Mhm.
Catastrophic forgetting is the elephant in the room for anyone working in ML right now.
Yeah. So today, we're tearing down the blueprints of deep learning. We're doing a deep dive into this incredibly radical paper from Google Research by Behrouz et al., and it's called Nested Learning: The Illusion of Deep Learning Architecture.
And it really is a radical shift. I mean, it forces us to completely rethink the boundaries we draw around neural networks. Traditionally, we heavily compartmentalize our systems.
Right, we put them in neat little boxes.
Exactly. We treat the neural architecture, the optimization algorithm, and the training data as distinct independent variables. But this research frames architectures and optimizers as a single, interconnected system of nested associative memories.
Which is huge.
It is, because by doing that, they provide a mathematical framework that naturally explains in-context learning. It exposes why current architectural heterogeneity is really just an artifact of our training methods, and it offers a literal blueprint for true continual learning.
So to set the stage for you, the core problem they're addressing here is, like we said, catastrophic forgetting. We've been operating under this brute force assumption that if we just stack more layers and dramatically increase the parameter counts to the trillions.
Which is incredibly expensive, by the way.
So expensive.
Yeah.
We assume generalized intelligence will just emerge from that scale. But adding parameters doesn't solve the fact that modern large language models are completely static post-training.
Precisely. They don't evolve. And to illustrate the severity of this limitation, the authors map the current state of LLMs to a specific neurological pathology, which is anterograde amnesia.
Oh, wow.
Yeah, in human patients, this condition typically follows a traumatic event or a brain injury. The patient retains perfect recall of everything they learned before the event, and their core cognitive functions remain intact, but
they can't make new memories.
right, they entirely lose the capacity to form new, persistent long-term memories.
So they are trapped in this permanent present. And honestly, that's exactly what an LLM is doing. The completion of the pre-training run is like that onset event of the amnesia.
That's a great way to put it.
Right.
Yeah.
The long-term memory, which is stored in the MLP weights, is totally frozen. You can feed it a massive prompt, and it processes incredibly complex logic right in front of you, but the second you clear that context window, the model just resets.
It extracts zero persistent knowledge from the interaction. None.
It's like having a brilliant savant with brain damage who just forgets everything the second you wipe their whiteboard clean.
Exactly. And to understand how to fix this, if we connect this to the bigger picture, we really have to look at how biological brains actually handle continuous streams of data without overwriting their foundations.
Right. The biological inspiration here is fascinating.
The authors draw heavily from neurophysiology, specifically neuroplasticity and multi-timescale processing. They point to hemispherectomy patients.
Wait, hemispherectomy, that's where they surgically remove half of the cerebral cortex to treat severe epilepsy, right?
Yes, which is extreme, but it's vital for understanding this, because the remaining half of the brain literally reallocates its resources. The neural networks dynamically reorganize so the patient can function normally.
They cram language, vision, and motor control networks all into the remaining hemisphere.
Exactly. And this tells us the brain doesn't rely on rigidly heterogeneous, dedicated hardware blocks the way we design distinct attention heads or, convolution layers. It's using a uniform underlying structure.
It's uniform. But how does a uniform structure manage entirely different types of information?
Through biological rhythms. Brain waves, you have fast gamma waves oscillating at like 30 to 150 hertz to process immediate sensory input. And that scales all the way down to slow delta waves at 0.5 to 4 hertz.
And the delta waves are the ones critical for consolidating long-term memories over time, right?
Precisely. The brain distributes the processing across timescales rather than spatial blocks.
Okay, so this brings us to a huge causal transition. If the biological brain is solving continual learning through multi-frequency brainwaves over a uniform structure, how do we translate those biological rhythms into a rigorous mathematical framework for deep learning?
That is the absolute crux of the nested learning, or NL, paradigm. Under NL, we completely abandon the concept of a machine learning model as a sequence of discrete spatial layers.
No more layer 1, layer 2, layer 3.
Right. Instead, we formulate the model as a set of nested, multi-level optimization problems. Each of these levels operates with its own distinct context flow, its own objective function, and critically, its own update frequency.
Okay, let's unpack this math because this is where the traditional boundaries really start to dissolve. In nested learning, training a standard MLP layer with gradient descent isn't viewed as an optimization process anymore.
No, it's formulated strictly as an associative memory problem.
Yes.
Yes.
So if you look at the standard gradient descent update, where you update a weight matrix by subtracting the learning rate times the gradient of the loss, you can mathematically rewrite that exact operation.
You can. It can be expressed as finding a matrix that minimizes the inner product of the weights, the input data, and the local error signal, plus, a standard regularization term.
Which totally changes how you visualize the training loop. I mean, it's not just an algorithm blindly tweaking numerical knobs down a gradient.
No, the network is actively functioning as a surprise-based memory system. It's actively memorizing what the authors call the local surprise signal.
It maps each data sample directly to the exact mathematical error of its own prediction.
And that reframing leads to a massive paradigm shift regarding the nature of pre-training itself. We typically draw a hard line between pre-training and in-context learning, right? We think of in-context learning as this emergent property that only happens at inference time across prompt tokens.
But under nested learning, pre-training is mathematically indistinguishable from in-context learning.
Exactly. It's just a learning module compressing its specific context flow, which in this case is the entire massive pre-training data set into parameters at the lowest frequency levels.
So it's doing the exact same associative memory compression, it's just doing it at frequency 0 once deployed.
Right. But this is where it gets wild. Because if backpropagation is just an associative memory actively compressing data into weights, we have to look at the optimization algorithms driving that process.
Oh man, this blew my mind. The ML key layer is a memory module. What does that make, Adam? Or stochastic gradient descent with momentum?
Under nested learning, known gradient-based optimizers like ATOM or SGD are themselves two-level nested associative memory modules.
Wait, really?
Yes, their job isn't optimizing per se. Their job is compressing the flow of past gradients into their parameters. They are just another memory block, exactly like the MLP.
Just that their context flow is gradients instead of tokens.
Precisely.
But wait, if optimizers are just memory modules for gradients, then do they suffer from limited context windows? Just like an LLM suffers from a limited token window.
They absolutely do, and it's a severe capacity limit.
Let's talk about the math of ATOM here, because this is wild. If you look at the geometric series for ATOM's standard beta hyperparameter, which is usually set to 0.9, the exponential moving average effectively zeroes out by step 43.
Right. The last 43 gradient steps account for 99% of the momentum.
So we are trusting the convergence of multi-billion parameter models to an optimizer with a context window of just 43 steps. It's totally blind to the global loss landscape.
It is. ATOM only remembers the immediate local curvature. It can't see the global landscape required to maintain persistent knowledge for long-term continual learning because its memory of the gradients decays in a rigid, exponential manner.
Which perfectly explains why fine-tuning destroys core reasoning so quickly. The optimizer forgets the foundational gradient landscape almost immediately and violently over-indexes on the new specialized data.
Right. It has no long-term memory buffer to anchor it.
So how did the authors solve this mathematically?
What's fascinating here is that they use this insight to build far more expressive optimizers. Specifically, they proposed delta gradient descent, or DGD, and the multi-scale momentum muon, or M3 optimizer.
The M3.
Yeah, and the mathematical upgrade here centers on gradient-dependent weight decay.
Okay, so rather than a blind exponential decay like ATOM's fixed beta, the decay rate is dynamic.
Exactly. The optimizer's memory modulates its decay based on the actual loss landscape it's navigating. So if the gradient direction is highly consistent, indicating a stable feature, the memory of that gradient persists longer.
Makes sense.
But if the gradient is noisy or contradictory, it decays faster. This allows the optimizer to capture complex dependencies across time without assuming the incoming data samples are independent and identically distributed, or IID.
Which is a huge flaw in how we currently train models on sequential data streams.
Exactly. The M3 optimizer takes us even further by operating across multiple timescales simultaneously, maintaining different buffers for fast and slow gradient updates.
Okay, so if the layers and the optimizers are mathematically doing the exact same thing, compressing their respective context flows, we have to confront the uncomfortable truth here. And here's where it gets really interesting, the illusion of architecture.
Yes, the title of the paper. When you combine the architecture and the optimizer into a single neural learning module under this nested framework, you realize that the structural heterogeneity we see is an illusion.
We spend so much time debating transformers versus MLPs versus linear attention or RNNs.
And they are all secretly uniform. They are simply feed-forward networks optimized at different levels and different frequencies.
This was the biggest aha moment for me.
Yeah.
A standard transformer is just an extreme edge case of nested learning. The self-attention mechanism operates at an update frequency of infinity.
Right, it's a non-parametric regression, instantly adapting over the tokens in the prompt.
Exactly. Meanwhile, the MLP blocks in that same transformer operate at a frequency of 0 post-training. They never update.
They are the exact same underlying feed-forward structure, just pinned to the absolute extreme opposite ends of the frequency spectrum. And because we've separated them into these extremes, we've created artificial bottlenecks.
So to fix this, the authors completely abandoned the binary concept of short-term versus long-term memory.
Right. Just like the biological brain doesn't have a rigid partition between short and long-term storage, our models shouldn't either. They introduce the Continuum Memory System, or CMS.
And how does CMS work mathematically?
CMS distributes memory continuously across a spectrum of frequency updates. It functions as a nested hierarchy. You have higher frequency parameters that adapt incredibly fast to new context.
Absorbing the immediate local surprise signal.
Exactly, but they hold that specific knowledge very briefly. Then you have lower frequency parameters that update rarely. But when they do update, they consolidate persistent knowledge.
And because the hierarchy is nested, it forms a continuous loop process. The information flows in both directions. Right?
Yes. The fast-adapting high frequencies buffer the immediate shock of new data, while the higher levels in the hierarchy act as persistent storage that actually meta-learns the initial states for the lower, faster levels.
So it allows partially overwritten or forgotten knowledge to be recovered, because the slower frequencies retain the broader structural patterns.
That loop is what enables true continual learning. The model is constantly shifting data between immediate contextual memory and long-term structural memory based on the gradient-dependent decay we discussed earlier.
Okay, the unified theory here is incredibly elegant on paper. But theoretical math doesn't always translate to performant code. How does this continuum memory system actually perform when instantiated into a real neural architecture?
They test this through an architecture they call HOPE. HOPE serves as the ultimate proof of concept for the paper. It combines the continuum memory system with what they term self-modifying titans.
Okay, let's break down what a titan actually is in this context,
Sure.
because it's a significant leap beyond standard attention or even modern linear RNNs. Standard associative memories have fixed hyperparameters that we set before training, right?
Right. But a self-modifying titan is an associative memory module that dynamically generates its own operating parameters.
On the fly.
Entirely on the fly. It computes its own keys, its own values, its own learning rates, and its own weight decays based on the input context it's currently processing.
That is insane. The network is calculating the data it needs to store while simultaneously calculating how fast it should learn that data and how quickly it should allow itself to forget it. It's entirely self-referential.
It is, and the empirical validation on this is staggering, particularly when you look at formal language recognition benchmarks.
Because formal language tasks are like the acid test for a model's ability to maintain state. Standard transformers famously fail at these.
Exactly. Take the A to the N, B to the N counter task.
Yeah. For you listening who might need a quick refresher, this is a classic context-free grammar test where the model has to track deeply nested states. It has to match exactly n occurrences of the letter A with exactly n occurrences of the letter B. It requires deep computational state tracking.
And a standard transformer scores between 0% and 46% on this. They fail completely because attention just diffuses over long sequences without a recurrent state.
But the Hope architecture achieves a perfect 100% across the board on the A to the N, B to the N task.
Yes, and on parallel parity tasks as well. It matches the expressive state tracking power of specialized nonlinear RNNs like LSTMs.
But LSTMs can't scale to massive language modeling because they can't be parallelized effectively. You can't train an LSTM on trillion token datasets efficiently.
And that's the breakthrough with Hope. Because of how the self-modifying updates are structured within the nested memory levels, it retains the parallelizability required to scale up across massive hardware clusters, just like a transformer.
You get the state tracking of an LSTM with the training efficiency of a transformer.
Exactly.
But this raises an important question regarding compute overhead. Whenever we discuss dynamic updates and continual learning across nested memory systems, the immediate concern is a computational cost.
Naturally, continual learning traditionally implies backpropagating through the entire massive network constantly as new data arrives.
Which is computationally impossible at the trillion parameter scale. Is the Continuum Memory System efficient enough for real-world deployment?
The math shows that it is highly efficient, largely due to fractional parameter updates. CMS only updates a specific, very small subset of parameters at any given time based on their frequency.
The 1 over F update mechanism.
Exactly. If a specific layer or memory module operates at a frequency of f, it only updates 1 over f parameters per training step.
Oh, wow.
Yeah, by scaling the frequencies logarithmically across the nested hierarchy, the total FLOP count remains remarkably low. You entirely avoid the bottleneck of full network backpropagation during the continual learning phase.
That's brilliant.
And furthermore, the specific update mechanism they designed unlocks sequence parallelization for the higher frequency levels. That mitigates the sequential bottlenecks that normally plague recurrent designs.
So what does this all mean for you listening? For the ML practitioners actually building and deploying these pipelines, this paper signals a massive structural shift in how we handle deployment. We're looking at the eventual death of the rigid pre-training versus inference binary.
We really are. Currently, we spend millions of compute hours pre-training a model, we freeze the weights, and we deploy it to inference where it immediately begins to slowly degrade in relevance as the real world changes.
It's static.
Right. Under the nested learning paradigm, future models will act as unified neural learning modules. There is no isolated pre-training phase and isolated inference phase.
The model exists purely in a state of continuous multi-frequency optimization.
It is always learning, always compressing, and always updating its parameters, just at vastly different speeds depending on the nested level.
So to recapitulate all these core breakthroughs, pre-training, in-context learning, and continual learning are fundamentally the exact same mathematical mechanism. They're just operating at different timescales.
Exactly. Architectures and optimizers are not separate entities designed in isolation.
Right. They're simply nested associative memories compressing their distinct context flows. Whether that flow is comprised of input tokens or gradient landscapes, the underlying associative compression math is entirely uniform.
And recognizing that uniform compression math leads to a profound observation from the authors regarding catastrophic forgetting itself.
This is wild.
As an industry, we treat forgetting as a bug, a flaw in our architecture to be engineered away with better regularization or larger parameter counts. But in a nested learning framework, forgetting is recognized as a mathematical inevitability.
It's the natural, unavoidable consequence of data compression hitting a finite capacity limit. I mean, a network with a fixed parameter count must overwrite old data to compress new data once its lowest frequency buffers are full.
Which fundamentally alters how we should approach scaling. We shouldn't be trying to prevent forgetting. We should be managing the decay rates dynamically, exactly as the M3 optimizer and the Hope architecture demonstrate.
Which leaves us with a truly provocative thought to explore on your own. If forgetting is an unavoidable mathematical inevitability of finite capacity, what happens when we attempt to build true, unbounded artificial general intelligence?
It's a daunting question.
Will the ultimate AGI require an infinitely nesting architecture? One that, as it runs out of compression room at its lowest frequencies, is capable of dynamically generating entirely new frequency levels.
It would literally be growing new latent tissue.
Exactly. Expanding its own mathematical capacity in real time to accommodate the perpetual flow of reality.
A truly self-constructing architecture. It's a fascinating implication of treating networks as living nested memories rather than static blueprints.
It really is. Thank you for taking this deep dive with us into the underlying mathematics of machine learning's future. Until next time, keep questioning the blueprints.